So today we'll be doing some MCQ based questions related to powder metallurgy, and this is a weeknight doubt clearing session. So the first question says that sintering is performed at dash to dash. That means we have to tell that it is performed at what temperature and the properties that we are able to achieve after the sintering process. So it is saying it is performed at the melting point of the major constituents, increases so that the final strength is increased. This is right because we need to increase the final strength of the compact that we are producing. The option second is that it is carried out at the melting point of the major constituents to decrease the final strength. This is wrong because we want a higher final strength for the compact. So all the decrease the final strength options are wrong because we are trying to increase the final strength. It says then above the melting point of the major constituents to increase the final, or below the melting point. So we have three options: at melting point, above melting point, or below the melting point. So the right answer is actually below the melting point of the major constituents, because the powder metallurgy concept is different from the casting process, where we are trying to achieve a final density of a material by not melting the material. We are not going to the molten state. That is a major difference between the powder metallurgy and the casting process. So we will be carrying out the sintering at below the melting point of the material, and we it will be helpful in increasing the strength of the compact. Okay. Then it says, in a broader sense, the term interface in sintering is used for dividing the grain boundary between the same phase, dividing the plane between the two different phases, dividing the plane between any two different grain boundaries, adding the plane between any two different phases, and adding the plane between the same phases. So we need to say, what does the interface in sintering mean? When you're talking about sintering, what does the interface mean? It is actually a plane that is dividing the two phases. For example, we have two phases that are undergoing sintering, and we will be having a dividing plane in between them, and that dividing plane will be referred to as an interface. Okay. Then it says that sintering connects the solid grains into dash monocrystalline crystals, amorphous solids, polycrystalline solids, or above. Obviously, when you're talking about sintering process, we are trying to achieve a crystalline structure at the end of the solidify at the end of the sintering process, at the end once you are done with the heat treatment process. So we do not want to have a monocrystalline structure, because such crystallizer actually produced through melting. These methods are produced, for example, if you know the formation of your silica, single crystalline silica, Si. So silicon, sorry, Si, single crystalline silicon, that is formed through monocrystalline solid formation. Also, we are not forming an amorphous solid; we are forming a proper crystalline solid. So what does polycrystalline mean? That means that there are different crystals that are present in the whole structure, and these crystals are oriented in different directions, so we can call it be a polycrystalline material. Okay. uh, Now the next question says, the particle bond together during sintering by increasing the surface energy, decreasing the surface energy, heat transfer, volume energy. So if you know, if you have a sintering process, you will have a compact, and that compact will be like this, and you're trying to, after compression, you have subjecting it to a treatment process where you are trying to fill in the voids between these grains or the crystals that are present inside this material, and you're trying to fill in the voids. So during sintering process, what happens when you are having you are having these two particles, say for example, during sintering they will try to form some liquid bridges if it is a liquid phase sintering, or they will form by solid solid contact, solid state sintering, if these two particles are in contact. So they will form some contacts between one another. So what happens actually, the surface energy that was associated with these two particles will decrease, because now these surfaces are not available to contribute towards the surface energy process. So in actually what they happen, they try to interact through solid state interactions, and their surface energy decreases. So we will have a decrease in the surface energy when you are going through sintering, because these two particles will come together through their boundaries, and their surface energy will be decreased. Okay, you know that when you have a large number of solids, for example, you have very large number of solids present in the structure, then the surface energy is very large. But if you have a less number of particles or less number of surfaces available, so then the surface energy will be less. Okay. uh, Now the next question says that higher sintering stress is possessed by 10 nanometer particles, 5 nanometer particles, 15 nanometer particles, 7 nanometer particles, and above. So the answer is that we have 5 nanometer particles where higher sintering stress is possessed. Because obviously if we have a very small amount of small size particles, the centering stress that will be acting on the particle will be more, because you know that if you have a stress is nothing, it is just, it can be force per unit area. So if you have a very small particle, then the stress will be very high. So you will having a high centering stress for 5 nanometer particle. Then we have another question that says, in which of the following stage shrinking of material is predominant in sintering? Okay, so what happens that we have a shrinkage of the materials taking place, because what happens when you are taking it in a the material which you have given of certain tolerance, you are giving a material of certain dimensions, and you are subject, this is a green compact, say for example. Now you are you are sintering in, now you have a sinter density of the particle, it has changed obviously. So this is your green compact and this is your sintered product. So what has happened during this, the density of the material changes. This is your green density, this is your say for example sinter density, right? As it moves from green to center density, the pores that were present inside the material, they are being closed, because now you are having green growth during sintering, and that green growth results in interactions between the grains, and then they prevent they led to the collapse of your pores, they led to the collapse of your any spaces inside the compact, and as a result you have a green strength. So contact is it the shrinkage takes place in the material, that means whatever the material dimensions you have taken, that will shrink because of this collapsing of your intricate shapes and pores inside your material. So in which stage it happens? There is one stage where you have a contact formation. As I told, we have a sintering process and then we have contacts formed at the material. So this is your contact formation, this is your stage 1. And then there is a neck growth. What is neck growth? Because when you are trying to get these two particles, for example, if you have this particle and then you have this particle, so as they come contact, first they try come to be in contact. Once they are in contact, then they form the neck. This is the neck region. That is, they try to form a coleus together, they form to form a region of togetherness. And then there is pore rounding, that is an intermediate stage, and then there is a pore closure stage. So which of the following will have a predominant shrinkage, right? So obviously in contact formation there will be no shrinkage. So this is not the, because this is just the formation of your interactions. Then there is a neck growth, but still there is no shrinkage happening, because the area that was present in stage 1 is still the same, only the particles have coalesced with one another, so there will not be any shrinkage, the area remains the same. But when you are going for pore rounding, where we have particles being accumulated in these neck regions from some other region, it will result in pore rounding. So this is the right option for shrinkage. So that means the shrinkage of the material takes place during pore rounding, which is an intermediate stage of your sintering process. Then we have the another question that says that the angle at the junction between two grains is referred as contact angle, dihedral, critical, straight angle, bond angle, wetting angle. This is a dihedral angle. This is what we have seen. We have seen that if we have these two grains and the angle that they form together between these two, this is called as a dihedral angle, that is at the junction between the two grains. This contact angle is actually related to your wetting properties, right? So for example, if you have a material and it is being wetted by some liquid, so then we will be saying that it has made some certain contact angle with the material. This is related to your wettability. So this is not related to your grains during the sintering process, right? Also, all other options are wrong. So dihedral angle is the right option. Okay. So now we have another question that says that broadly there are dash different types of mass transfer mechanisms, and densification is given by dash transport mechanism. Obviously, there are different types of mass transfer mechanism. One we say that there is a bulk transport, one we say there is a surface transport. So there are different types of transports. So we can say there are actually two types of mass transports, and the densification that occurs during the sintering process is actually based on the bulk transport, right? So the option A is correct. Then we have select the incorrect statement related to the bulk transfer mechanism in sintering. First, bulk transport moves the mass from inside to deposit on the pores. Okay, so we know now the sintering happens and there is a densification process that occurs through bulk transport. We need to say what happens actually during this bulk transport. It says that it moves the mass from inside to deposit on the pores. Bulk transport repositions the mass on the pore surface to lower surface area. Bulk transport produces no growth without the change in contact spacing. Surface diffusion is dominant sintering mechanism in bulk transport, and grain boundary diffusion is dominant sintering mechanism in bulk transport. So the right answer is bulk transport moves the mass from inside to deposit the pore. This is right, because what happens if you have a grain like this, it will tend to have uh, bulk transfer phenomenon by the material that is present inside. If there are any material present inside, it will try to be deposited at these neck or at your say for example, mm, at your places where there are pores, so those pores will be filled. That is how the densification process will take place. So it will try to transfer the mass from inside to deposit on the pores, so all the pores will be filled, and then we'll be having a bulk transport. Next, when the neck has been formed, so there will be a growth in the neck. So the growth in the neck is that if you have a starting like this type of particle, then you will move to have something like this, something like this. So you have a higher neck, this is your neck, and then we have this neck. Okay, so you'll try to have a increased neck growth, and that also takes part with the help of weld transport. Then we have surface diffusion is dominant in centering. In obviously once the neck has been formed, then it is the surface diffusion that takes place to result in the formation of bulk transport. Okay, then we have surface energy loss during sintering is evident by the reduction in surface area, particle bonding, decrease of the pores, all of the above. So obviously, as we said, that during sintering or during densification process, the particles come in contact with one another, they form a neck, and that neck grows so that the particles coalesce together, and there is a decrease in the porosity, and that decrease in porosity will result in your densification. So if surface energy loss is there, that means there is a decrease in the surface energy. That is obviously because of all of these factors, because it is reduction in the surface area. Obviously, as we said that as the surfaces come together, there is a reduction in your surface area, the particles start bonding together, and there is a decrease in the pores. All of these contribute towards decrease in the surface energy, and then we can say that densification has taken place. Now the next question says that the neck growth in sintering is dash control process. Is it plastic control? Plastic flow? Is it mass flow? Is it thermomechanical? Obviously, it is not a thermomechanical process, right? Because we are not going to any mechanical forces that are being imparted during the sintering process. It is not a thermomechanical process. So, is it diffusion controlled? Is it plastic flow? Plastic flow means that there is a change or there is a deformation in the material that is taking place. While mass flow is that we are only having a change in the mass, that flow of the mass from one location to another. So here the right answer is diffusion, because once the growth has taken place, once the neck has been formed, that growth in the neck takes place only because of the diffusion of the atoms, and there is no further mass transfer. The mass transfer is happens before the neck formation, where the mass is being transferred from its from that location to a places where there are pores or crevices. So it is said that it is a diffusion controlled process. Then we have another question that says, which of the following characteristic the doping additive should not possess? So, if you have a doping additive, which of these things should not possess? Because we are trying to have added to the like sintering process, and we are trying to increase the responses of densification. So if it will segregate at the grain boundary, it will be a process. It will be create a place of high chances of fracture. So, for example, once you are having the segregations at the grain boundary, this will act as a site of failure for further mechanical processing or further any application. So, the segregation should not take place. Okay. Okay. So then we have formation of low melting point phases. Obviously, it should not. It should. The formation of the low melting point is important. So here we have the characteristic that the doping additive should have. It should not. It should segregate at the grain boundaries. Okay, and then it should form also a low melting point phase that will result in the formation of the liquid bridges between the grains, and then it will result in sintering of the molecule. So however, it should not produce very high atomic weight, obviously, because these, if they are producing high atomic weights, it will not be able to uh, form an association or a coalescence between the two grains together. Okay, and then it should also have high solubility. The equilibrium vapor pressure over the neck is dash the particle surface. Is it less than the particle surface? Is it greater than the particle surface or equal? So the vapor pressure that it should be near the neck, it should be less than what it is at the particle surface. And then we have another question that says the process of sintering will stop when this is actually a relationship between your surface energies and then surface surface areas between the particles. So we have solid, so SS means that we have a surface energy between solid and the corresponding area, and then we have a surface energy between a solid and a vapor phase, because there is a pore that is being filled, or that the mass transfer occurs during the sintering process. So then there is a surface energy between a solid and a vapor, and then corresponding its area. Okay, so you have to say what is these relations the same. You have to say, is it equal to 0, is it greater than 0, less than 0, or equal to 0. So actually what happens when you have a this neck formation. So for example, if you have two particles, first we'll try to see this, then we'll come to this, because here we say that the neck that is being formed, that is making a concave uh, angle, right? There is a concave process between at the neck, so this is concave, while as if you have a grain that is convex, right? This is convex while this is concave. So these, there is always a difference in the vapor pressure. So the vapor pressure at your neck will be always less than at your neck will be less than the vapor pressure at your say for example at your surface. So the results in the mass transfer and the surface tension. Okay, and then we have process of sintering that will stop when we have the total surface energy is conserved. That means the surface energy of your solid and solid vapor, the summation of the two is equal to 0. So that means whatever the surface energy that you are creating in the form of a solid during the sintering process, that is actually notified by the decrease in your energy from the solid vapor interface. So that would be, you can have overall like this, that the surface energy of your solid and the corresponding area of your solid plus the surface energy of your solid vapor and the area of your solid vapor is equal to 0. So if it is equal to 0, then this will be equal to minus surface energy of your vapor dAsB. So that means whatever the decrease in solid vapor interface you are seeing, that will be because there is a solid solid interface being created. So there at the expense of your closing of the pores will be having a solid solid surfaces created, and those solid solid surfaces will result in densification. Okay, then we have to achieve the densification during sintering without grain growth. So we want to achieve the densification and we do not want to have a grain growth, because what happens when you are giving a temperature during sintering, there is a possibility that once these grains come together, they will try to coalesce and they will try to form a bigger grain. So it will result in a recrystallization and it will result in formation of fine coarser structure. So we do not want the formation of this during the sintering process. So what should be the value of your surface energy between the solids? It must be what should be the value, while the surface energy of your vapor must be what? So actually what happens, you should allow the solid surface energy to be maximum. That is why if it is maximum, then you will not be allowing the surface to coarsen, you will not allow it to grow, while the surface energy of your solid vapor must be minimized, right? So you have two things. You have that your solid surface energy should be maximum, while your solid vapor interface and interface energy should be zero, because that then we'll be able to achieve a maximum densification during the sintering process. Then we say when the powders of similar composition are sintered, physical interactions are dominant. When you're talking about similar composition, the sintered, that means we are having a single phase, right? So they are trying to what are the physical interactions? You know that when you are having, say for example, you are having two phases. You are having one phase and you are having two phase, and this phase, if it is melting, it will act as a liquid phase. So then you can say it is a liquid phase sintering. So the interactions will be because of the liquid bridges that are formed between the two molecules, right? So there are some liquid bridges that are formed, and that will result in the sintering of the molecules. But in case of similar composition, where we have only, say for example, a type of molecules, so what will be the physical interaction? It is dominant due to the particle size ratio. Okay, so we have another question that says in activated sintering, the qualities of the activator are uh, uh, in activated sintering, the qualities of the activator are must dissolve, must be insoluble, and must add rapid interface transport path. Actually, when you are having an activator sintering, the qualities of the activators are that they must dissolve, right? They must be insoluble and must add rapid interface transport path. Actually, this activator is such that it will be able to dissolve in one of the phases that you are taking, and it must be insoluble, not because it has the property of activating your compact. So it must not be insoluble, it should be soluble, and it must add rapid interface power. Definitely it should add rapid interface transport part that will help in your densification process. So your option A and your option C are the right options. Okay. Okay, so then we have one question here that says which of the following are the criteria for the activators? It must be a metal which forms a low melting phase, right? That's why we said it will form a low melting phase and then it will act as a pathway for the diffusion, and compound which forms a low melting phase. Obviously, it should form a low melting phase and it should segregate at the interfaces, because that will help in closing down of the pores. So all the three options are essential for a criteria for activator. One, that it should be soluble, it should form a low melting phase. Two, that it can be also a compound, right? It can be a metal or it can be a compound of a low melting phase, and then it should also segregate at the interfaces. Okay, so all the three options are right. So that is all for this. Thank you.